I've just been reading about something that affects us every single day of our life, and it's something we hardly ever think about. And I'm referring to the force of gravity. Now I'm going to do a very simple scientific experiment here with this ball that I have in my right hand, and when I open my fingers the ball drops into my left hand. Now I did say it was going to be a simple experiment, but the question is, why? Why does this happen? Well, on the face of it, it's pretty obvious, isn't it? But it's only because we've been conditioned through millions of years of evolution to accept it as being obvious. And gravity is a concept that's been baffling the great scientific thinkers for centuries. Aristotle, Plato, Copernicus, Galileo, they all pondered gravity and didn't really know what it was. And I suppose the first person we think of when we think of gravity is Isaac Newton. Now, Isaac Newton was a very clever man and did lots of experiments with gravity and formulated some very useful laws of gravity and motion that we still use today. But the fact is, Isaac Newton did not know what gravity was. In fact, he didn't have the slightest idea what gravity was, not the foggiest. And it wasn't until a chap called Albert Einstein came along, and you've probably heard of him, that we began to get a handle on what gravity actually is. And it turns out that this universe we live in, that we perceive to be in 3 dimensions, is actually a 4-dimensional universe. To describe it properly, it needs the addition of another dimension. And Albert Einstein called this a 4-dimensional space-time continuum. Now, before you switch off, because I know that's a really scary term, and it's enough to frighten anybody away, but I'm no mathematician, and it is possible to understand these concepts by using analogies. Now, a really good analogy is the concept of flatland. And you have to stretch your imagination now and try to imagine a universe that's completely flat. This hypothetical universe is utterly flat. It has length and width, but it has no height, no up or down. And all the people that live in this flat land, they're also flat. And they live on this flat planet. A bit like this coin. We'll call it Planet 2D if you like. And they live on this flat planet in their flat houses, and they go about their flat business, and they go to their flat universities and they learn flat geometry. And they could tell you what a square is, but they would have absolutely no idea of what a cube would look like. They could describe a circle to you, but once again, they would have no idea what a ball or a sphere would look like. Or they would know what a triangle is, but they wouldn't know what a pyramid was. Their universe is completely flat. Actually, it's a bit like this sheet of paper. But although their universe is completely flat, what they don't realise is it's not completely rigid, it's a bit flexible. And what that means is, when we place their planet in their universe, it tends to distort the fabric of their universe, and it creates this depression in the fabric. Now the effect of this is that anything that comes into proximity with their planet will tend to slide down this slope until it reaches the bottom. Now the Flatlanders will see this going on and they'll say, well, yeah, that's gravity, isn't it? But they won't really know what it is, because to describe this universe properly, you would now need the addition of a third dimension, depth, to accommodate this curve. And of course, they have no knowledge of this third dimension. Now, it came to pass in the fullness of time that one of these Flatlanders was a bit smarter than all the others, and he said, well, I know what gravity is. There's another dimension, there's a third dimension, and it's allowing our two dimensions to flex. And of course, all the other Flatlanders, they were very sceptical about this bizarre idea, and very few of them believed him. But in the fullness of time, they came to accept his theories, and they were scientifically proven. Now, I don't know if you can see where this is going, but it's a very good analogy as to the situation we find ourselves in, where we live in this, what we perceive to be a three-dimensional universe, but in fact needs 4 dimensions to describe it properly. And of course, the smart Flatlander in our universe was Albert Einstein, when he formulated his theories of relativity and general relativity to accommodate gravity. Well, the way gravity actually works is that every material object has a certain amount of mass, and one of the properties of mass is that it has the ability to bend or distort the fabric of space. Gravity is a very weak force, and in something the size of this ball it would be almost unmeasurable, although it can't be discounted. Something the size of the Earth, of course, would have quite an appreciable amount of gravity, an amount that we define as 1g actually. And of course, something the size of the Sun, well, that would have even more gravity. So I suppose you could think of space as being a bit like a weather map actually, where all the stars and the planets are creating these local areas of low pressure, if you like. So the next time you see something falling, what it's doing, it's trying to get to the bottom of this local depression in space. Now, this 4th dimension, what does it look like? It's very hard to imagine a 4th dimension. And I have read that the 4th dimension can be considered as being at right angles to the other 3. Now, before you try to imagine that, I would say don't bother, because I've tried and quite frankly there's not a lot of future in it. It might help to have a look at the other dimensions and see what they are. So if we start off with a single point in space having no dimensions, just a point, that's 0 dimensions. We take that point and we put another point next to it as close as we can, and then another point next to that as close as we can, and we keep on doing that, and we keep extending these points into infinity. We finish up with a straight line. Well, that's 1 dimension. That's our first dimension created. And to create two dimensions, we'd have to take that straight line, put another straight line on top of it, another straight line below it, and keep on doing that ad infinitum, and we would have created two dimensions. We'd have a two-dimensional universe, like this piece of paper again. Now, to create a three-dimensional universe, what we need to do is to take this plane, or this membrane, and put another one on top of it, and then put another one on top of it, and keep on doing that to infinity once again, and we will have created our three-dimensional universe. Now, where does this fourth dimension come in? Well, if we consider any material object, this book has length and width, and it has depth. It has three dimensions. But to have a valid existence, it needs one more extension. It needs an extension in time. It needs to exist in time. So when we talk about the fourth dimension, what we're talking about is time. And every material object has to exist from moment to moment, doesn't it? It's a progression of moments. And if we go back to our dimensions, they were all progressions, weren't they? The first dimension was a progression of points to make the line. The second dimension was a progression of lines to make two dimensions. The third dimension was a progression of planes to create three dimensions. So surely it must follow that the fourth dimension is a progression of the other three dimensions. The other three dimensions, in other words, it's a progression of moments in time. And that's what the fourth dimension is. And when we add it to the other three dimensions to create four-dimensional space, which incidentally we should now be calling space-time, it's the proper terminology for it. Anyway, I think I'll sum up by saying that yes, gravity is a distortion in space caused by the presence of mass. And Albert Einstein worked all this out on a piece of paper. What a clever man he was.